So holomorphic from all of C. Okay. Suppose that x is b greater than or equal to 1. And this is real greater than or equal to 0. Mm. Mm. C times 1 plus absolute values. Right. Okay. Okay. Mm. Right. Right. Yes. Right. 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 And hmm, hmm, right. Hmm, 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 hmm. And that goes to zero, right? So it's easy. That's well. Yes. Or wait. So there is still some problem because uh, yes, if you take it, okay, that this is less than equal to absolute value of this, right? And then if you put that bound, then there is 1 plus mod z d, right, that is fine. And here you have mod, so this is r, right? R to the n plus 1. This is also r to the n. So this is r. Okay? And there is another r here, right? Because of this one. Uh, right. And then this is integral over the unit circle, right? That will become unit circle, right? Or or yeah. Okay. All right, that's fine. So it is this, and yeah, okay. This is also n plus one, so that takes care of the d plus one, right? So if n is bigger than d, then zero. So this is all. I mean, this cannot be one. So approximations. So this is fine. Which problem? Yeah, we didn't actually complete. We just did two parts, and the other parts we just sort of glanced through together. Yes. Yeah. Yes. Sure. Sure. Mhm. Uh, yes. So if I just give you the definition first, uh, just to have something to say. So like the triangulated category tau, rather this th, not tau. So t T is an additive category. And additive category would just mean that it's a category whose home sets are abelian groups. Yeah, home sets are abelian groups, and finite products and co-products exist, and they are the same. So that will take us. So one can start with various different ways. There is also a way using pre-additive categories, but you can just start with this additive category. Okay. With a functor, which is denoted like this. So this is going to be a functor from the category to itself. Okay. So this is an endo. This is what is this kind of functor would be called an endo functor. So maybe I should not put it like that. And invertible functor. So this is also invertible. Yes, that is main thing, that this also has an inverse, sigma inverse, whose composition would be, you can call it identity. If you know equivalence of functors. Otherwise, for the moment, yeah, you can just assume that it's invert. Yes, I mean the composition with the inverse. Yeah, there is another functor, so the composition is both ways is equivalent to the identity functor. Right. So you have this thing. And a collection, or rather, not and, but with with a collection, maybe T of diagrams called triangles of the form, collection of diagrams form, this form. So F, G, H, satisfying F composed G equals G composed F equals H composed sigma F. So sigma F will become a map from sigma X, suspension is called suspension X, to no, suspension X to suspension Y, because it's a functor, so it will take F to sigma F suspension, and these are all zero. And this is called a triangle because if you interpret this suspension X as a kind of X, as a variant of X, right, then it's kind of a triangle. But the definition. This is the definition. But then you see, this is just a collection. Okay, so a collection of diagrams. So this collection of diagrams is part of the information of the triangulated structure. Okay. So when you say, that's what I should say. Yes. Yeah. So they all belong to that J, and these morphisms are. So this X expected. Okay. And this collection of diagrams. Furthermore, this collection of diagrams should satisfy some conditions. Furthermore, T satisfies the following. So number one is this, and right, is that following. This is in T for all X in the category J. And number two, given any X, Y in the category, also F in the category, and morphism, okay, there exists object which we call, denote by this. This is called the mapping. But yeah, this is at the moment just an object such that this with F, and there will also exist morphisms, is in T. Okay, so this is the one is like the triviality one, which is all the trivial triangles, trivial diagrams are in T, which is also called as the trivial pre-triangles. So any diagram which satisfies this composition thing, you can call it a pre-triangle. And those which are designated to be in T, we call that triangles. So these are pre-triangles, and we say that all the trivial pre-triangles are in T. And this is the second one, that any morphism can be completed to a triangle. And this is actually unique, but it has to be seen later. It's not so obvious that the CF is unique, but yes, so there is. So that's the mystery, that a lot of strange things happen. A lot of things, the definition is sort of still maybe quite big or small, whatever, but it has a large number of consequences. So, but anyways, the third one is what is called a shift axiom. These are in some way axioms called. Yeah, that's wrong. I should have. Yeah, the notation suggests that, but that's not correct. It needs x and y, of course. I mean, it certainly. Yeah, actually, it's not clear from my notations, but yeah. I mean, yes, it can be built only from f because when you give f, then you give x and y also. So yes, answer then is yes. And the third axiom is the translation axiom. Name. So just write the property is that is this that if this is in T, then it implies so here you have G H, then this implies that this is also in T. And there is a little bit of thing, the signs change due to some reason which becomes clear when one considers examples. And in fact, it works both ways, but the other direction actually follows from this direction. So that's the third axiom. There's a fourth axiom, and then there's a fifth axiom. The fourth axiom would be a completion of morphisms. So that would involve two triangles. So that any morphism can be completed. So we have this. This. And these are just two triangles. And given, so there I've written T. So given, so I should say, given this, where these are in T, and this two things, and hence this also by the functor, there exists a morph like this. So that is a point. So this exists. So this is again an axiom which is not completion. And then there is a fifth axiom which is called octahedral axiom. Yeah, now that also has a variant which can be based on 4. So there are two equivalent ways to put it. Let me just say yes, yes, right. The diagrams are communicated. And right. So the last one is the octahedral axiom. So, um, so this is related essence, but let's see. So given this in T, and of course, so we have one triangle, we have another triangle. We stick to that notation y1, z1, and then we have this. So this x is the same. This x is the same, and it can be upgraded automatically, but it is writing it the traditional way. So given this now, of course, this not of course, but this is identity, and then this let's say that this is also given. This And now we are supposed to have three triangles. So this is the third triangle. Sorry, so this is going to be one. Yeah. So suppose this situation is given, and yeah, this situation is not complete. This situation is given. Suppose this situation is given, then of course this morphism Z to Z1 is there. By one of the previous axioms, by the second axiom, it can be completed. Okay. But here we are claiming that it can be completed in such a way that this is also a triangle. This thing. Okay. So I would say that, yeah, that this can be completed in such a way that this is also a triangle. Okay. Which is yeah, which is not so obvious, I think. That's means it doesn't usually happen. Doesn't happen if you don't put it in the action. And right, and of course the last one, so this will become suspension square. Okay. And there is something. So this is called the octahedral axiom. Such that all the diagrams are commuting. So you see, we start with two triangles. So I start with, yeah, this one triangle, this triangle, and this triangle, and these morphism. I mean, this basically, I mean, this morphism again, exists by the previous action. So one can say that, yeah, basically that it has to be, yeah. So the axiom should be that, yeah, that you can also arrange for this so that arrange for this, yeah, that's important, arrange for this so that this thing is a so that this triangle which you get, right, is such that this thing is also a triangle and everything comes. So that's, yeah, basically I should say that this one is the main thing. So this is actually should not be given. Yeah, I'm just not saying it in the correct order by going or correcting too many times, but you see, this is the point that this morphism can also be arranged so that, you know, when you complete it to a triangle, and then this turns out to be isomorphic. Or maybe you don't, yeah, like that's what it means for this to be triangles. Or you can just say from the definitions, you know, you can just say that this is so that this is also a triangle. That is not so obvious. Yeah. So yes. Because this morphism is not unique, not clear that it is unique, right? But there is, yeah, but you can arrange one so that once you have this, then in a way, then also you don't know yet. We don't know yet that this is unique. So you can say, you can arrange for this and this so that this vertical thing is a triangle and this is also a triangle. So this is this is just the definition. Maybe with examples it becomes more clear. Maybe give the example next one. Yes. So, yeah, and if you want to read, means if you want to have the time to read, then you can just also read from this book. So Neiman's book, and just type Amnon Neiman is here the is right. So well, so it's useful basically whenever you have what are called derived categories. Whenever you have a derived category, then it is useful. And why? So, what first of all, what is a derived? Why a derived category? So, um, say that like you're doing these sheaves, right? So if you fix a ring and then consider all, so the ring, and then you have a structure of a sheaf on that ring, three sheaf, and then you will have a structure of a sheaf, and then that becomes a what is called a scheme. But let's just call that, and then now if you have now there is a notion of sheaves over that sheaf, okay, or basically modules over that ring, let's say, modules over that ring, then you would often like to consider chains of modules. Even to understand one module, you would like to consider chains of modules, right? So yeah, right. So yeah, your objects are chains of modules, and then you have a natural notion of morphisms and so on. And right, and then there is like once you did this homology, right, simplicial homology. So you would like to say like this, that if there is a morphism between between two chains, two infinite chains maybe, such that that morphism induces, that morphism will induce a morphism in the homologies, right, of the domain and the range. You have to change, so you have homologies by at every point. So it's the nth point. Now the homology at nth point for the domain and the codomain. If the morphism you had, if it induces an isomorphism, then you would like to call that original morphism also an isomorphism. Now, if you want to do that, obviously why you want to do is quite clear, because if you want to study things only up to homology, you want to have a theory where you want to investigate homologies of things and not all the other rich structures which could come in the way. And they're nice, but cannot handle them at the same time. Then you would obviously want to consider those morphisms which induce isomorphism or homologies. You want to call them also isomorphisms. So now it's clear that you have to change the category because you are changing the nature of the morphisms and so on, right? So when you change the category, what you will do, you'll be quotienting something or something, right? So like when you do a ring and you localize a ring, you want to invert. So you want to take some collection of objects, take some elements in the ring, and you want to call them invertible, right? So when you call something invertible, you have to do some kind of a quotienting to the ring, or what you call localization to the ring. Why quotienting? Because when you invert some things, you inevitably make some other things zero. That is some phenomena which you might be seeing, right? So A is zero in the localization if A times this is zero. Right. So it is like a quotient procedure in some way. So now this new category which you get is done by now, but this becomes complicated for a category. For everything to be mathematically precise, it becomes complicated. And now we see that this kind of procedure needs to be done in many places. So you might need to do it for in topology, so topological spaces, if some map is there, then a map between the chain complexes like you once did. And there you might need to do the same thing. You might need to do this in various different places. Right? But the fundamental constructions seem to be the same, right? Which you are doing, and the categories which you will end up with, they also have some similarities, and all of them actually will satisfy these actions. Okay, and so we make this definition, and then we prove theorems about triangulated categories in generality, like just axiomatically. Obviously, with motivations coming from those examples. Like one example coming from algebra, right, and motivating some theorem. But the theorem you get will now be applicable in topology or in representation theory, wherever. So this is, you understand, this is the technique. Just like we have groups were invented and then groups are now used everywhere. So something like that. Yes. So they are very, very useful, and they are useful in many other ways to, I would say, many other ways to motivate it. But different people would have their own motivations. Physicists might have some other motivation. They have something like a mirror symmetry, which you may have heard, homological mirror symmetry. So they would have some different motivations. Obviously, I do not know, and but you should, if you know, then you should try to search. Yeah, but everybody has their own motivations. So triangulated categories are also useful, and some structures in physics are also like triangulated categories. But since I don't know very well, I could not say. But then it turns out that even triangulated categories these days are in a way obsolete. In a way, I would say in a way obsolete, because now there are things called infinity categories, which in a way, yeah, they actually, as much as I understand, they actually carry all the structure of triangulated categories. I don't see why triangulated categories are have anything more to give us than infinity categories. Only obstruction may be that not everybody is willing to yet learn the infinity category. Like I don't know anything about infinity. So that is one of the things. Like people working in different subjects, not everybody might be willing to learn that. But it is the, I think it has replaced triangulated categories. But it then yes, yeah. But they might be wrong. There might be things where triangulated places where you have a triangulated structure, but you may not have an infinity category structure. But I don't understand where what is required. Like for example, I do algebra, so for me, triangulated categories are in finite dimensional algebra. So, eh, so this is a book by Happel, a person named Happel, and the name of the book is Triangulated Categories in Representation Theory of Finite Dimensional Algebras. So here the applications are quite different. They have some other rules, but here also triangulated categories have. So, so it can be used in different cases. Anyway, yes, and I don't know the other. I just know triangulated categories in this. I don't know how triangulated categories are used in topology or how they are used in algebraic geometry. I don't know. I only know the abstract theory and some applications in modular representation theory and some applications in representation theory of finite dimensional algebras. Other places I don't really know. But yeah, it would be, there are some things which would be useful for me. Yes. So these are the things. Yeah. So anyways, let's meet on Sunday then.